All right. Hi, everyone. My name is Farbad. I'm a data scientist at AT&T Chief Data Office. And today I'm here with Mohem and Nick from RelationalAI. We are going to present how AT&T combines generative models with knowledge graph for better AI accuracy. I would give an introduction to AT&T CDO, and Mohem will continue the introduction for RelationalAI. Just to summarize all the generative AI use cases at AT&T is everything related to GenAI comes through a platform we have called Ask AT&T. The main reason behind it is it's a hub for us to centralize all of the model deployment, all of the model inferencing, all of the observing the model when it's in production, all of the training, and essentially every single part of the application lifecycle needs to come through Ask AT&T because it helps us to organize everything a lot better, and also it's a safer way to have one gate for everything. Over the last 3 years, we have onboarded over 100,000 customers. Basically, the user of Ask AT&T are AT&T employees because it's an internal tool. And we have fine-tuned 90 models. The most recent model that we have fine-tuned is for generating summaries for call transcript between our agents and our clients. AT&T has over 240 million customers, and we get over 300,000 calls a day from those customers, which they may have a problem with a network or they have a question. Those calls get summarized in a different way for different purposes. Like one of the goals that we have is if our competitor name is being mentioned in that call. We don't need a generative model to know if the competitor name is being mentioned. It's a simple regex expression. But we do care, we need generative models to understand the context around when the competitor name is being mentioned. For instance, there could be a case that there are potential customer for us. So they are with another company and we can actually approach them. We say, hey, we have this deal, we can have it cheaper, something like that. So those calls get summarized, and that was the most recent fine-tuning that we have had. We have 410 production agentic workers. Essentially, with a company at AT&T size, that we have somewhere over 140,000 employees, and there are multiple departments. So when someone creates an agent that is in production, we want to make sure we do not duplicate effort. So when I say agent, it's most of the times a language model wrapped inside an API that has access to certain tools and has certain skills. Once we deploy that, we want to make sure we can reuse it. So if another department wants to do the similar thing, they can either modify the same agent or just use it as it is. And one of the recent agents that we have is the graph rag with RelationalAI. So essentially, if a department within AT&T has an ontology and they want to talk to it, they can use Ask Graph to talk to their ontology. Or if they want to generate one, create one, a hand-curated one, we can still work on it and then deploy it and use Ask Graph. Another example is there's so many departments within AT&T, they want to talk to their documents. The document could be any unstructured data in any format, JSON, Word, PDF, it doesn't matter. And we can essentially, we have an agent that they can upload the documents and they can do Q&A. On average, every single day, AT&T experiences around 450 million API calls, which is roughly around 4 billion tokens a day. That is across all of the use cases that are in production, and we have a lot of calls. For instance, just the summarization use case is around like 40 million API calls a day because there's so many people and there's so many, the same conversation gets summarized in different ways. We do have 71 production RAG plus fine-tune use cases. The difference between production, RAG, fine-tune, and just a fine-tune model is the fine-tune model are usually just a model with an endpoint that we just hit it and we just get a response from it. For instance, the conversation hit the model endpoint, we get the summary. There is no retrieval process involved. But for RAG and fine-tune is, for instance, for a customer care. When someone calls AT&T and has a problem regarding, let's say, iPhone 14 troubleshooting for their network, that has a certain document. So our agent can actually talk to the chatbot and get the related document, and it would generate a response for our agent. And they are there to verify, to make sure their information is correct, and they actually respond to the question. So that 71 are RAG and fine-tuned. And last but not the least, we've experienced 20% coding efficiency since using generative AI models in production. And that 20% comes from the number of completed user stories that our developer have had. So what we've seen is it takes the same amount of time for them to complete a user story, mostly software engineers, but they're able to complete more user story in a given day. So that has improved 20% there's a 20% efficiency in that regard. In 2024, the return on investment for all of the generating use case within AT&T all involved has been 2x. And it is estimated to have around $3 billion plus saving by end of 2027. One of our other GenAI use cases is ask data. So essentially, you ask questions from your tabular data. You may have questions, you're looking for information. And it is very common within AT&T leadership that they encourage employees to evaluate themselves against open source benchmarks. The main idea is we want to compare ourselves, let's say, with Google to see how well they perform on X and how well we do perform on X to make sure we have a state of the art in production. Regarding that, we have tested our ask data methodology against 2 open source benchmarks. One is called Aspire 2.0, which recently it was a joint effort between RelationalAI and AT&T. And as of 4 days ago, we are number 1, and number 2 on it is a Snowflake AI research team. And there's another benchmark called BERT SQL, which AT&T again is leading on that text-to-SQL benchmark. And there's a lot of companies, including Google is number 2 as of now, Contextual AI, Alibaba, IBM, Snowflake. Mostly big tech companies try their technique and solution on this benchmark. But there is a caveat. These benchmarks are a lot easier than what's happening inside AT&T. So the databases that we have a lot more fields, have a lot more tables, and it gets a lot more complex to deal with. With that in mind, I will pass it to Mohan.
Thanks, Farbad. Hi, everyone. So we love that AT&T has the intellectual honesty to kind of want to compare itself to others and sort of baseline sort of the performance. But what Farbad said is absolutely right. The real world is much, much harder than these benchmarks. And of the 2 benchmarks, Spider is much, much harder than BERT. And the real world is harder in 2 ways. One way is that real world databases are much bigger and much more complex. So it's not uncommon for us to deal with real world databases that have thousands of tables and millions of columns of information in them. There's, just like code, the data has similar problems and schema has similar problems around missing or incomplete or out-of-date documentation. Field names are cryptic, table names are cryptic, there's no description. People make changes to the schema, but they don't reflect the changes back in the documentation. So the database is operating under one set of assumptions and the documentation is something different. There are very inconsistent use of data formats. So sometimes dates are stored year, month, dates. Sometimes it's date, month, year. Sometimes people will use strings to put a bunch of information in there in a random way. There are lots of complicated joins across many different columns with conditional values and different transformations. You heard earlier today in the keynote discussion of the importance of semantics for AI. You don't have typically the semantics. They're very opaque. They're usually computed outside of the database and you don't know what's going on. So there are a whole bunch of real-world concerns that you have to deal with when you're dealing with things that are not always captured in these benchmarks. There's also, in some of these benchmarks, you get more metadata than you can get in practice. Yeah. And if you're going to generate it with humans, the humans are obviously not free. And sometimes the domain experts and the SMEs are actually not up to speed on how to represent things in a database. Okay, I think for this audience, I don't think I have to oversell you on this. I think we all know how messy real-world databases are. The second dimension where these benchmarks sort of fall short relative to real-world use cases is that the questions they are trying to answer are much easier than real-world questions. Okay, that fundamentally these benchmarks map to either RAG or text to SQL. And the real world questions can go beyond that. So for example, how do I troubleshoot a customer's fiber service connectivity issue? That's something you can imagine answering with RAG on textual documents. You embed the question, you search, use a vector database similarity search, and you find the piece in the documentation that gives you the answer. Or a question like, what was our postpaid wireless net addition in South Central region last quarter? Again, you can imagine answering that with text to SQL because it's about something that already happened and you want to be able to sort of generate the SQL query that will answer that question. We saw a lot of that earlier today in the keynote, and we think there's a lot of sophistication, emerging sophistication around that. But what happens when you start asking questions about future sales, like how many fiber installations are we projected to complete in the Northwest region next month? That's not in your database. That's not a SQL query, right? Or what actions can our retail store teams take to increase mobility upgrades in the Northeast region? Or how should I price a product or a service in a way that maximizes market share or maximizes profit, et cetera, okay? These types of questions are harder to answer than you can find in these benchmarks. And as I said, they cannot be answered with one simple reasoner working against one type of data. You have to look across many different types of data. So the bottom layer in this layer cake here, you have to sometimes to answer one question, you need to combine data from tables, data from textual documents, data from JSON documents, data from graphically structured things, and images. You have to look at data that lives inside the enterprise versus potentially combining it with third-party data, like the data you can get on the Snowflake marketplace. And then the data formats themselves can be proprietary or it can be open formats like Iceberg and so on. Okay? So I don't think I have to sell you very hard on the fact that you need to look across different data types as questions get more interesting. Of course, I don't think I have to sell you on the fact that you need more reasoners than just SQL and a vector database, right? You want to be able to reason over graphs, or you want predictive reasoning, or you want prescriptive reasoning. The kind of reasoning that leads you to leverage predictive models and integer programming solvers and so on. You want to be able to reason in a rule-based way, okay? Furthermore, these are just skills. These are just reasoners that you use, but you need to be able to describe to either a human agent or a machine learning agent what your business is about, right? So you need to be able to say, here are the core concepts and relationships between them. I have customers, I have wireless towers, cell phone towers, I have suppliers, I have distribution centers. These are things that the model, like your new employees and your language models don't know how AT&T runs. So you need a description for that. And you need to be able to generate as much of that description automatically as possible because you don't have time to sit down and write it all down. And you get sort of that description from a variety of sources, including your databases, as well as your documents, as well as code and applications and so on. Now, this semantic layer, that's the third layer in this layer cake, comes in two flavors. Today, we heard a lot about a very important flavor, which is the dimensional semantics. These are the semantics like semantic views in Snowflake that were basically modeling the world as dimensions and metrics. dbt has some flavor of this, Looker has some flavor of this, AtScale has some flavor of this. These are semantics that you specify to do AI for BI, okay? However, the kinds of questions we have to answer, like what's gonna happen and what to do about it, are usually answered in applications. People program pricing applications or replenishment applications or wireless network optimization applications. And you need more expressivity than you can get in a dimensional model. Most applications are not programmed or built on top of dimensional models. They're built on highly normalized and object-oriented and relational schemas, okay? And so folks that are in the application game, like Palantir and ServiceNow and SAP and Glean and Writer, they will pick a relational or a knowledge graph abstraction to be able to model the business, okay? And then when you have that all in place, you need to be able to use these assets to teach the agents, the language models, the employees, what your business is about and what tools are available. And that's typically done with fine-tuning. And you can fine-tune, especially the open source models, to teach them to do all this stuff. Okay? So with that as context, this is what we're about. We're basically looking to supercharge question answering with relational knowledge graphs. And we are using LLMs to aid in the refinement and knowledge capture, which is in turn is used to do fine tuning of the LLM, which then makes it better at knowledge and knowledge capture. And it's a virtuous cycle, and you go on and on. Okay, I already explained briefly what a knowledge graph is, so I'll skip that for now. And there's more information about us at various talks that are happening at this conference and previous summits and previous Snowflake events. If you're interested, you can look some of this stuff up online. So with that, I turn it over back to Farbad to tell us more about how this is done.
Yep. So there are multiple techniques for whenever you wanted to do text to SQL, and most of these techniques are available internally at AT&T. Not everything was applied for a Spider, but overall, this is the story of how we were able to lead on that leaderboard, which is basically text to SQL. I will explain 1 through 4, and Nick and Molhan would explain 5 through 9. It is briefly the story of how can you transfer text to SQL with a relatively high accuracy. The very first step when it comes to text to SQL is data profiling. Data profiling essentially means if you want to create or enrich the column description. There are many cases, especially in real world, you do not have the database schema. So the column description doesn't exist, and you have millions of fields that unless you have the domain knowledge, you have no idea what's inside that field. So the way the data profiling works is you generate a statistics and you profile every single column. So you look at the number of rows in that column that the data exists, the number of null values, the number of distinct values, the mean of the column, the max, the median. You even look at the most common variables like the top K. And then you generate an English description of all those entities, of all of the description. There is no GenAI up to this point. So it's simply looking at the statistics of a given column and put it in a plain English that a language model understands. The next step is you can use even a small language model like 8 billion to generate a column description using this information. Or if you already have a column description, you can enrich it. So basically, this is the current column description. This is the statistics that you're getting, and then you generate a much more enriched column description that really helps with retrieval. And just to give you a few examples of how it helps is the top 2 examples are very similar column names from AT&T metadata. So for instance, let's say we want to know how many fiber customers do we have in the state of Texas. And a language model understands in order to generate a SQL query, it needs to filter down the database in the where clause of the SQL query to only include the state of Texas. But the question is, are we going to have the state of Texas in 2-letter TX, or are we going to have a full name? The language model doesn't understand that. How can you actually pass that information? And that usually comes from data profiling. So these 2 columns are in the same table of the same database. And if you notice, the first column, the state names are 2 letters, TX, CA, or FL, so Texas, California, Florida. There's another column in the same database that for whatever reason, the people who created it first, they decided to include the entire state name with a capital for the first letter. So we need to really mention that for the language model in order to perform better. The last example is from BERT benchmark, actually, which numeric identifier for a school, it is something that comes from the benchmark itself. That's a column description. What data profiling has added is it's a 14 character. So if we were to look for a specific county, the district, a school, that would really help the language model to formulate a SQL query. So, if you are interested to learn about the database profiling overall more, this is a paper from a research team at AT&T. They have had over 30 years of experience in database research. They are the Bell Labs people, and they are still doing database research up to this point. I would encourage you to read this paper. It explains a lot more in details than I just explained. The next step is a schema deduplication. So the main goal for a schema deduplication is you need to reduce the token that exists in the database schema by just removing the duplicated information. It usually happens in time series databases. You have tables that it includes the same information, so the fields in it are the same, but you have that data over time. So you have the same column name, column type, column description over and over and over for different time frames. And the main idea is how can you compress this information? So you can start with creating dictionaries of full table name, column type, and column description. And the way to compress it is like this example. Let's say this is an example actually from the Spider benchmark, that initially the database schema has around 7 million tokens. 7 million tokens is a massive amount of information to process. So the idea is, if you look at those tables, they include exactly the same column names, the column type, and column description, but they have one table per day for a couple of years. So you can easily compress that information to, on the slide in the after. So instead of having one table name, you pass a list of table names to the language model. So the language model understands that all of these tables have the same schema. And in just one example for a Spider benchmark, we were able to reduce the number of tokens in that given database from 7 million to 156,000 tokens, which is a lot more manageable number when it comes to language models. And if you're interested in a schema deduplication, Snowflake has a paper on it. It's the AI research team, and they explain, it's a slightly different approach they've done, but overall, they explain in a lot more details for this approach. Next thing is schema linking. So after we enrich the column description, after we dedupe the schema, now we have a very it's like a trim version of the schema. Now we want to do a schema linking. The main problem we have right now is the full database schema. It can easily overflow the context length of most of the language model. And even if you're using a language model as GPT-401 or the recent Llama 4 that has a very long context length, you still are overwhelming the language model with a lot of information that not all of them are related. Not all of them are essential or necessary to respond to the question. So the goal of the schema linking is trim down the schema to the parts that is actually related to the question. So schema linking needs to be done per question. It genuinely has to look at the database schema, see which parts are related, and bring it down. And the way we've done it is you would need to pass the entire database schema to a language model and generate a query multiple times with different approaches. If you're using the same model, you would need to change the seed number and the temperature and generate the query multiple times. If you have access to multiple models from different resources, you can just generate one SQL query per model. And the main goal is to extract the field names and the table names from the generated query. So when you generate a query, it does not matter if the query is correct. It does not matter if the query can actually run against the database, because the main goal here is to trim down the schema. It's not to have an accurate query generated. And if you find that related table name, it's called table linking. If you find a related column name, it's called column linking. And together they are schema linking. Just to give you an example, these two queries were generated for a Spider benchmark. It doesn't matter if they are correct or not, and it doesn't matter if they can actually run. All we care is what columns language model decide to use, what tables language model decide to use. So we can get those. And in that way, the same example that I explained in the previous slide, that we went from 7 million to 156,000 for the duplication, for schema linking brings down the token size from 156,000 to only 8,000. And this is just the results of table linking. We did not spend too much time on column linking on a Spider because table linking was just working fine. So essentially, we were able to identify the tables that the language model keep using over and over, generating a query for a given question. And if you're again interested to learn more about schema linking, there's a lot more in it. This is the same paper that I showed in the previous slide. It's from AT&T database research team. And they have a lot more details on how they have done it. Next step is now we have a key-rated trimmed version of the database schema, and we have the question. So it is now the time to generate the final query that we need for a given question. The main problem with all this language model is they just predict the next token. So they, based on the context you provided, they generate the next token. And they're all prone to hallucination. So the main goal of self-consistency is how can you ensure the query that you're generating is actually consistent, is actually accurate. The idea here is there are basically two main approaches. Number one is just with prompting. So in your prompt, you would encourage the language model to consider multiple reasoning paths. And you would also include that after consider multiple reasoning paths, only generate one response. It would increase the number of tokens the model would generate and also would process by maybe 5-fold. So instead of 2,000 tokens, you could be generating 10,000 tokens because the model would consider multiple reasoning paths. But it has shown evidence that it helps with response generation. One other way is, on top of adding to the prompt, is it's very similar technique to schema linking. You ask multiple models to respond to a SQL query, or you ask the same model multiple times with different temperature, seed number, or even you reorder the schema, you shuffle it randomly. And the main idea is, let's say you have 5 generative responses. You can do either a popular voting at this point to see which response has been generated, maybe 2 out of 5 or 3 out of 5. You will be more confident for that given response, or you can use just another language model, most likely a reasoning model as a judge. So you have multiple questions with the same schema and you have multiple generative response. You simply ask a reasoning model to decide which response is better. And just to give you an example is, it is a simple question. This is actually a slide, it's a picture from a paper from Google. And this is just the main idea. Let's say there is a simple question. You're doing a simple mathematic calculation. If you ask LLM a couple of times, one of those, it could hallucinate. So let's say if you ask 3 times, 2 out of 10, if the 2 out of 10, it generates the same response, it's most likely going to be, that's going to be the accurate response. And if you're interested in self-consistency overall, that's a paper from Google. I would encourage you to read more. They have a lot more details in it. And with that said, I will pass it to
Take it from the podium.
Nick.
Thank you, Farbad. Yes. So I would like us to zoom out a little bit now. If you're given a database, you have the schema, you want to do schema linking, follow all the steps that Farbad mentioned, everything is fine. But what if you don't know even in which database the query can be answered? Or if you know that database and that database has 1,000 tables and, I don't know, 20,000 columns. So I don't know if you remember that paper came from Uber last year, where they kind of like took the whole stack of text to SQL and they mentioned this problem, or where can I even find my tables and my columns? So we want to address this issue. And for that reason, we would like to see, is it possible to kind of index all the metadata we have from our databases, especially for an organization like AT&T, the number is like astronomical. And, you know, as you all know, one of the state-of-the-art methods for search and retrieval in GenAI is GraphRag, something also introduced by Microsoft a year ago. We're all familiar with RAG, but we all know that if we build a knowledge graph on top of our schema or metadata, anything you have, nodes, whatever you can find, then you can do much better. And RelationalAI is into the knowledge graph business. And for that reason, we went and we implemented an end-to-end system, a GraphRag system, natively in Snowflake by using all the components of Cortex, Cortex AI, Cortex Search, Cortex Analysis coming soon, from scratch. A fully transparent system that you can audit, you can reuse its components. All of it runs on SPCS. Nothing leaves your security perimeter. So you do that. That's like a perfect way of retrieving the tables. You can use it in accordance to what Farbad described. But there's another problem so I don't know, when you join a new organization, you're a data scientist and you want to solve a problem, and says, where's the data? I say, well, here's a database. And you look at the database and you don't know where to start. So quite often, we find this question, like, what does my database have? Again, Moha mentioned what we heard in the morning about semantic views and semantic layers, how important they are in terms of knowing what you have. So if we pose this question, what is there in my database? We would like to get some answers that they have to do with concepts and relations. And the easiest way to represent them inside a database is with views. Views is something that SQL understands. And in this particular case, that's actually from a Snowflake marketplace, a free database where we run this. You might want to have concepts as regular customer, intern, or staff that generates revenues. Although in some companies, interns also generate revenues anyway. So knowledge graphs, like building that semantic layer, actually helps a lot forming SQL queries. Because when you give something to a language model, and most of the times if you do the analysis of your errors, you see that the harder, the more complex the SQL query you need to write, the more likely it is to fail. So you kind of want to keep that compact. You want to avoid nesting. You want to avoid any operators that can lead to errors. And frankly, any of us, if we had to write a big query, we would have to create some intermediate views, okay, to handle that. And here's an example. I'm not going to get into the details, but where you start with a query which is large, and as you're building the views, you're making the query more compact. And this is actually what we are targeting for. We don't want to use SMEs to create all these views. Typically, the views are created by subject matter experts, but in the age of agentic AI, we want to put the agents to do the hard work for us, okay? So here's kind of like one version of our tool that uses for agents. We've added more, and depending on the problem, you can have a different combination. That's all you need as a subject matter expert, to define the roles of the agents. And then you let them do the job. And like when you build a language model, you do that in a self-supervised way where we are saying predict the next token. Here you're saying create views that can make the answers, the SQL queries, more compact. This is kind of what you're targeting for. Now, of course, in many cases, that might not be enough, you know. So you give a database with hundreds of tables to an agentic framework, and they use common sense to derive some questions and some answers, and with that create the views. If you happen to have, so that's completely unsupervised. If you happen to have some sample questions with answers, that helps a lot. It even helps if you just have the questions, or sometimes the queries. So in order to address that, we actually ported this agentic framework in SPCS. We use Autogen 2. Again, Cortex AI and SPCS services. And that's something that we have in an experimental mode right now. And we went another step further because we know that a lot of people like Cortex Analyst. And one of the challenges sometimes is like, how do you set it up? How do you prepare the semantic views? So we're actually forcing the agents to take another step and also create the semantic views for you in order to be able to set up your analyst and move forward. And you can find more in our paper from last year's NeurIPS tabular representation workshop, and we're actually preparing a more recent publication on the issue. So, as I mentioned, the schema refinement, it works better when you have some type of information, and what every organization has is the query logs, okay? That's like easy to access. And query log analysis, even when you do it mechanically, just taking your query logs and looking at how tables are being joined, you can find, you know, foreign keys that they're missing from your schema. or all of the stuff that Farbad mentioned that they are trying to understand with data profiling. If you have access to query logs, that can help a lot. And there are some examples. You can find more at the AT&T paper that has been mentioned a lot about how you can use that. It's just that in the competitions, we didn't have access to query logs, but every organization does have access. And to take a step further, the query logs are good in order to find schema information or semantic information that is missing for you. But it's also very interesting because you can just go, if you take a query log and you give it to a language model, it can actually find the question that this is answering. That's an easy problem. And in fact, in the paper that we keep referencing, there are some ideas about if you augment it with relevant schema and some extra metadata. You see here the example that, that's an experiment that by using these techniques that Farbad mentioned before, you pretty much get a benchmark of 86, I think, queries. For 13, you make a better question than a subject matter expert would have expressed, 68 good and 2 good minus. So it's pretty good for actually training your schema refinement. And with that, I'm going to invite Moham to talk about, in my opinion, one of the most important aspects that is coming up. Everything we talked so far happens in the prompt. But what about fine-tuning? I think there is a lot to do over there and a lot to discover. So Moham, if you want to.
Okay, yeah. So Nick, I'll need your help on a slide here. So,
okay, I'm here for you.
For those of you who don't know what fine-tuning is basically taking a language model and teaching it a little bit more than it learned by the model creator. And obviously in the context of what we're doing, we want to teach it about the databases that it's answering questions about so that it can do more for us and doesn't require as much information in the prompt, okay? So your two choices are when you want to tell a language model something, you give it context in the prompt or you fine-tune it, okay? The more you tell it in the prompt, the more work it has to do at inference time to parse all that stuff. And so the more time and the more compute and the more cost it takes to give you the answer, okay? However, if you want to teach it by fine-tuning it, now you have to spend the time and compute to fine-tune it, but that's usually an offline task. That's something you do in the background, not while people are asking questions in real time, okay? So we're really trading off like, hey, when do we want to spend the time? When do we want to spend the money to train a language model? So there are, broadly speaking, two approaches to fine-tuning, supervised fine-tuning and reinforcement learning fine-tuning. You might have sort of read about sort of reinforcement learning as becoming like an emerging technique for fine-tuning. Nick, you know?
Yes, so 8 months ago were the whole frenziness with reasoning and this next leap we took with language models. Obviously, reinforcement learning became very fashionable and it really proved itself. And you see here the post from Alibaba, like embrace reinforcement learning. And whenever someone tells you to embrace something, somebody else is coming and say, hey, there's also the supervised way. So this is from Sky Nova or Nova Sky. I don't remember. It's from Berkeley. It's a lab. I always confuse that. Where they actually said, well, let the bigger model do the chain of thought, and with supervised fine-tuning for $150 only, you can do as well. You can do really, really well. In my opinion, there's a way to embrace both. I'm not biased towards one or the other, and I think that takes us to the different approach to fine-tuning.
Yeah, so we're introducing a new approach to do this. So it's not something, fine-tuning is a broad label. We're introducing something that we're calling superalignment. Superalignment is a term that has been used by others. In particular, OpenAI used it to say, hey, we want to align these models with human values, and we want to protect ourselves from superintelligence. But in this context, we're basically using it to, define it as follows. We define superalignment as designing effective and efficient alignment algorithms, aligning the language model with what we're trying to accomplish, to learn from noisy labeled data, okay, so point-wise samples or pairwise preference data, to align their objective with the human objective, okay? And do that in a scalable way when the task becomes very complex for human experts to annotate. So we're trying to teach these language models a lot about our business through these knowledge graphs that we're creating, and so we need to, we need to change the way we fine-tune to accommodate that, okay? And the term naturally falls out of sort of alignment and superintelligence. And really, when we talk about super alignment, we're talking about having it learn the skills needed to answer questions, including learn how to use these reasoners that go beyond SQL and a vector database. So they use a predictive reasoner, prescriptive reasoner, graph reasoner. We haven't talked to you about those today because that's the open benchmarks don't ask these types of questions, so we don't have a baseline to discuss with you. But it also is useful to actually learning some of the 8 skills that we covered. These super alignment can actually teach you to do elements of data profiling and elements of schema linking and elements of schema refinement and all of that kinds of those kinds of things, because you're teaching the model how to answer these questions. Okay. The nice thing about doing things via fine tuning is that you get sort of better response time at question answering time. So Farbad has measured this to be a little bit better than I'm reporting here, but if you take a fine-tuned Llama 3.3 70 billion parameter model, you fine-tune it on one GPU, the time it takes to get an answer to your question is about 11 seconds. If you try to take that same model and tell it in the prompt everything it needs to know to answer a question, it might take up to 8 minutes for it to parse through all that stuff. Okay? So the second choice, you didn't have to do any fine-tuning, so you didn't pay for GPU time then, but you pay for it at runtime. Okay? Here are some examples of us applying this fine-tuning to different dev data in the BERT SQL benchmark. You can see as you do more and more super alignment that the results get better and better, but it takes about 5 GPU hours per super alignment iteration. And here is another example of running this over the super alignment, the BERT SQL benchmark, and doing it, combining both, in this case, only data profiling, which is one of the 8 techniques, with super alignment. And you see that the results get better and better. We didn't tell you how we ended up, because this hasn't been submitted, and the results are really good, but we're not going to announce them until we actually have a submission. We're working with the BERT SQL folks on that. And here you can see on just one of the databases, not all of the databases here, just one of them, you can see how super alignment on its own can learn to do effectively a lot of the things that we described earlier today. Okay, so in closing, we talked through 9 different techniques that we use to supercharge question answering, and we talked about how they're used for realsies at AT&T, but then we also referenced sort of some research, the published research, to give you a little bit more pointers on what what to do if you want to explore this stuff yourself. We also talked about the fine-tuning step, which is sort of a new contribution as well into this world, making these systems much more practical in terms of response times. Farbad talked to us about all the great work that AT&T is doing. I mean, Generative AI has only been around for 2.5 years, and to be able to do everything that they're doing here and be on track to create $3 billion of value is amazing. And then I talked to you about the work that we're doing in terms of adding support for real-world databases and real-world questions that you don't get so necessarily in the benchmarks. Okay, and with that, we just close with a quote from Sam Altman yesterday. He said, the Platonic, I just thought it was very interesting when they were asking about the future and where this is all going. He said, the Platonic ideal is a very tiny model that has superhuman reasoning capabilities and can run ridiculously fast on 1 trillion tokens of context and access to every tool you can possibly imagine. All right? I don't know if you watched that talk, but you remember him talking about how where we're going is in a couple of years, you'll be able to sort of give these things, ask questions of the language model, like, what should my business plan be for the next 12 months? What's the price target for a particular company's stock and so on. These are not easy questions to answer You need lots of different applications, lots of different people to answer these questions. And so you can imagine a language model that has been fine-tuned and super aligned to do to your business and learns to use all the tools, all the reasoners, all the skills, okay, can actually start to tackle some of these questions. And express quick gratitude here to the team of folks that worked on this, spanning a lot of different organizations. So you've met Farbad and Nick. Greg actually is in the audience, and so he led the effort on super alignment. Naila, who's not here, was also involved in that. So was Sudhya. And then we have a bunch of folks from AT&T and from RelationalAI, I won't name them all, that were instrumental to the work that we described here today. So with that, we're unfortunately at time. I don't know if they'll let us take a question or two, but we'll be around here afterwards. You can ask us. Thank you very much.